So I want to talk a little bit about the derivative of an inverse function, not necessarily an inverse trig function, because this comes up on the AP curriculum as well, and we don't do it often enough to really get a good understanding of it, I think, a lot of times. So we know that part of it, we have a trouble with notation. So if we have a function f of x, then we know that its inverse function, we use this notation f inverse of x. Part of the problem is to talk about the derivative of the inverse function. It's usually written this way, and you can see you've got all of these little tick marks that are all just at different angles. And so what oftentimes is done is people will just say, well, let's say g of x is the inverse of x, and then we don't have to worry about the notation getting in the way of our understanding what's trying to go on in what's a kind of a tricky idea anyway. So if we do that and say that the inverse is we're just going to call g of x, then what is true about functions and their inverses is that they undo each other in the sense that if you plug a number into one function, say the inverse, then the original function evaluated at that answer undoes the changes and you get back to the original. And that works both ways. So we are going to, in particular, just look at this part of it here. So if we start with our f of g of x, and we're understanding now that g is this inverse function, then if we take the derivative of this, we get a chance to use our chain rule derivative. So we take that derivative of the outside function, leave the inside function alone, times the derivative of the inside function, and the derivative of x is 1. So this g prime of x now is exactly what we're talking about. That's that derivative of the inverse function. So if we solve for that g prime of x, the derivative of the inside function, we can divide that other mess, the f prime of g of x, to the other side, and this becomes our formula for finding the derivative of an inverse function. So we can find the derivative of the inverse even if we can't actually find the inverse function itself. First, let's just clarify and see what this means with a function that we can find its inverse. So we're going to look at a simple version of this where f of x, our function, is x squared. Now we know that this is a parabola. So a full parabola isn't going to have an inverse because a full parabola is going to fail that horizontal line test. It's not a one-to-one function, therefore its inverse would not be a function because it would be a sideways parabola. So we fix this problem by restricting the variable and saying that x has to be greater than or equal to 0. So visually what we see now is here is our function f of x. So it is only that right side of a parabola. And in particular, if we look at where x is equal to 3, then f of 3 is 3 squared is 9, and so we have that 0.39. Now we also can see that if we find the inverse, we can actually do this here. So if we start with our y equals x squared and x greater than or equal to 0, we can switch the x and y, which is how we like to find an inverse, and then we can solve for y, and we would get positive or negative square root of x. Now we can see in the graph of the original function that both x and y are positive, so we are going to not use the negative part, but say our inverse function is going to be just the positive square root of x, which we know is going to look something like that, and hopefully we recognize is the reflection in the line y equals x, which is what inverses do. So at our point 39, so at that point 39, we know that our f prime of x, that's now the derivative of the original function, is 2x, which means that f prime evaluated at 3 is going to be 6. So what we're saying is that somewhere over here at, say, I'm going to estimate right there is 3. Then we're going to be up here at the point 39. Then our claim is that our slope of the tangent line to that original function there is 6. Now, when we look at the corresponding point on the inverse, so now if we plug into our inverse, we plug in the 9, we get square root of 9 is equal to 3, and so we can see the corresponding point on the inverse function is going to be when x is equal to 9, and that is going to give us that point over here, which is 9, 3. We can see that the derivative of our square root function is 1/2 x to the negative 1/2, which is 1 over 2 square root of x, so that our derivative of our inverse, evaluated at x equals 9, is going to be 1 over 2 square root of 9 is 1/6. So the claim then is that the slope of the tangent line here, let me choose a different color. I'm going to go with the blue again. So the slope of the tangent line here is 1/6. So you can see that they are reciprocals of each other, that the slope of the tangent line at its point is going to be the reciprocal of the slope of the inverse function at its point, which is what this is actually saying. Okay, so let's see how it works in practice. So let's pick a different one that's going to be a little more challenging, perhaps, because we don't have this nice ability to find its inverse. So we can say that f of x is going to be x cubed plus x plus 1. So, and we're going to be interested in finding the derivative of the inverse at 11. That's our challenge. Now you can see, I hope, that if you try to switch the x and y and solve for y, you're going to be in deep trouble. We just can't do it. So we're not going to be able to. So here's where we have to know then, and I'm going to recreate it again, that if we say g of x is going to be our inverse function, then we know that f of g of x is equal to x, which means if we differentiate there, we're going to get our chain rule derivative. So it's f prime of g of x times g prime of x. And then if we solve that for g prime of x, which is our derivative of the inverse, then we get to our formula, if you will. So I think it's easier or more lasting to remember the process than to just try to memorize this formula. I would not recommend just memorizing it. So at any rate, what we're looking for is what is g prime of 11, which means we need to find 1 over f prime of g of 11. Now, in general, the hard part of this whole thing is figuring out what in the world is g of 11. Because we can't find f inverse, because this just isn't cooperating, we need to not try to find the whole inverse function, but just find the inverse function evaluated at 11. That's what this is really saying. G of 11 means what is f inverse of 11. So remember, an x value for the inverse is a y value for the original function. So what we want to do is set 11 equal to x cubed plus x plus 1. Now in general, these are going to have to be calculator active problems, because in general, this is not going to be something that we're going to be able to solve. You know, we don't have a great way of factoring a cubic in general. And so what we want to do then is use the zero finding capability of our calculator to find this value. So the idea is you will put this into your calculator as y1. You'll graph this function, then you will go to calculate the 0, use that option, and that will, if you do that correctly, will get you to x equals 2. So if x equals 2 for the original function when the y value is 11, that means that our f inverse of 11 is 2. It switches the x and the y's. So all of that work was just to figure out what that value is. And that's in general going to be the hard part of this. So g of 11, f inverse 11, we have said is 2. Now all we have to do is figure out what is f prime of 2. That's not a hard question because here's our f of x, which means that f prime of x is just 3x squared plus 1, which means that f prime of 2 is going to be 3 times 2 squared plus 1. That's going to be, let's see, 12, 13, I believe, which makes our derivative 1/13. Those are tricky.